In today's session, we'll be understanding the characteristics of synchronous motors. Uh, in the previous session, we discussed the open circuit characteristics and the short circuit characteristics obtained using the open circuit test and short circuit test performed on a synchronous generator. Uh, for us, we'll now see the characteristics of a synchronous motor. First characteristic is the torque speed characteristics. So what happens? We derived this equation yesterday, where induced torque in the previous session we derived this equation where torque induced is equal to 3 Vp Es sine delta divided by xs omega m. Thrice the terminal voltage, the induced voltage in the synchronous machine, sine of delta divided by the synchronous reactance into omega m. Note here that in a synchronous motor that the rotor speed is equal to the synchronous speed of the machine, that's 120 f by p. So this will be constant for a synchronous motor. Unlike the case of an induction motor where the speed varies, in case of a synchronous motor, the rotor speed will be simply the synchronous speed of the induction motor. It will only work at the synchronous speed. So whatever is the synchronous speed, we'll be able to obtain the rotor speed accordingly. So what we can see here is here is a synchronous value of the speed at which we'll obtain different values of the torque. So omega does not change, omega is constant. It will be the synchronous speed as this, but the torque will increase from 0 to a maximum value. We defined the maximum value of induced torque at sine delta equal to 1, that's at delta equal to 90 degrees. We said that maximum value of torque induced can be 3 Vp Ea divided by xs omega s in this case now. So accordingly, we'll have a rated value of torque and we'll have a pull out value of the torque. The maximum or the pull out torque will occur at delta equal to 90 degrees. But for normally the case is that the full load torque, the rated value is much lesser than the maximum value or the pull out torque of the machine. The pull out torque may be somewhere around 3 times the full load torque or the rated torque of the machine. So this is the torque speed characteristics. We can see that as the field current will increase, EA will increase. That means torque will change in this system, and also that will set a new maximum value of torque. So with respect to omega, the variation of torque is something like this. Torque rated simply means the full when you are applying the full load, the rated value of load to this machine, the rated value of load at which rated current flow through this synchronous machine, whatever torque is available at that time. That's the rated value of the torque. Full load torque is maximum value of torque obtained from this machine. Normally, normally the full load torque is nearly 3 times the maximum value of the torque, the rated value of the torque. Uh, and we can see this EA can be changed by varying the field current. So this torque induced will change. It will change with respect to changed EA. The maximum value will change with respect to changed EA. But omega in itself for a synchronous machine is constant. That is the synchronous speed of the machine. Now the synchronous speed can be any value. It can be 3000 RPMs, 1500 RPMs, 1000 RPMs, depending upon the number of poles and the frequency of operation. So this is the torque speed characteristic. The second type of curve that we'll be seeing is the V curve of the synchronous motor. Now, this V curve of a synchronous motor is actually the effect of the field current, uh, how the field, how the armature current will change with respect to field current for different power factor values in a synchronous motor. It's a variation of IA versus IF. These are the variation of IA versus IF in the case of the short circuit characteristics for a synchronous generator. Now IA versus IF plotted for a synchronous motor, and that also for uh, different power factor loads. So, what happens with the changing IF in the case of a synchronous motor is when we change IF, when we increase IF, EA will increase. Uh, an increase in IF, however, does not mean that real power will increase. Real power will remain constant. As the load of the machine is not changing, real power will remain constant. Real power will only increase when the load torque or the load applied on the synchronous motor is increased. Uh, Also, the terminal voltage Vt will remain constant. We already know that for a synchronous motor, Vt is the applied voltage. That's why it's constant. Vt will be equal to Ea plus Ia XS J J times Ia XS. We are assuming that there is no armature resistance at this time. So if Ea is increasing, Vt is constant, Ia all has to decrease for Vt to remain constant. So with increased field current, in case of a synchronous motor, Ia will decrease. So let's really see how this operates using the phasor diagram. This is the terminal voltage Vt. It will remain constant. Initially assume a lagging power factor. That means IA is in this direction. We are assuming there is no armature resistance, so IA XS will be somewhere here. This will be IARA. IA axis will be somewhere here. That means somewhere around this point. So this is IA axis. So accordingly, our EA will be here. This line here shows the curve IAXS at this point. It's 90 degrees to this. Uh, so the resolution of these two vectors gives us EA. I will rub this off. So this is my VT, and somewhere around here is EA. So let this be IA1, this be EA1. Power is constant. Power, we have derived two equations for power. VTE, 3 times VTEA, VPEA, sine delta divided by xs, and power is also equal to 3 VP IA cos theta, where delta is this angle and theta is this angle. So VP is constant in both the cases. Power is constant. EA is what varying. That means since xs is not changing in the system, so sine delta has to change in such a fashion that EA sine delta altogether remains constant. So from this, since power is constant, VP is also constant, xs is also constant, EA sine delta is also constant. And from this equation, since VP is constant and P is constant, that means IA cos theta has to remain constant. So what's happening here is that as we are changing now the field current, EA will increase. An increased EA has to but take place with has to be in such a fashion that EA sine delta remains constant. Now what is EA sine delta? Here is this vector. This vector is EA sine delta. So this vector has to remain constant for power to be constant. So what happens is as we increase the field current, EA will increase, the magnitude of EA is increasing, but EA sine delta will remain same. So this is EA2 now corresponding to an increased field current. EA2 will now be here. If we increase field current more, EA will now be here, EA3. EA4 will now be here as we increase the current further. So with increased field current, the induced EMF in the motor, because the field current is increasing, but the real power is remaining constant. For that to remain constant, EA sine delta has to remain constant. Also, uh, so this is how EA is varying with respect to uh, change field current. Now, what will happen but to armature current? Uh, Let me rub off these lines. Now we know where EA, EA1, EA2 stand. As we are increasing the field current, we assume that for this equation to be valid, this equation to hold true, what has to happen is IA has to decrease. So IA has to decrease, the magnitude of IA has to decrease, but what has to remain constant is IA cos theta. Now what is IA cos theta? IA cos theta is a vector in this direction. This is IA cos theta. So this has to remain constant. So as we are increasing the field current, IA will tend to decrease. IA will tend to decrease, and at one point it will become equal to IA cos theta. Now, if we further increase IF, the field current, what happens is IA will not decrease now, IA will start increasing. Now, this is because the power factor of the machine has changed. Initially, the power factor of the machine was lagging. Cos theta was it was corresponding to a lagging power factor. Now the cos power factor has become leading. So we are seeing the effect of IF on IA is this, that in the lagging power factor, IA will decrease with respect to IF with increased IF, but in the leading power factor, will tend to IA will tend to increase with increasing field current, and the minimum value of IA obtainable is at unity power factor when IA is equal to IA cos theta on the diagram. Now this is uh, now we have established that the real power has to remain constant. That means IA cos theta has to remain constant. So what happens is that at lagging power factor, IA will tend to decrease with increased field current, but once we reach the leading power factor, IA will now start increasing with increased field current. So we can uh, show the variation of IA with respect to IF now as this is IA, this is IF. IA is initially decreasing, then it's increasing. Fine. So this is at a unity power factor. This is at lagging power factor. This is at leading power factor. There's this kind of variation seen. IA will decrease in the lagging power factor region, it will increase in the leading power factor region, and it will have the least value at unity power factor with changing field current. So this plot is showing the variation of IA and EA using a phasor diagram as IF increases. So the terminal voltage remains constant. For power to remain constant, this vector has to remain constant. That is actually nothing but ES sine delta. And for power to remain constant, this vector that is actually nothing but IA cos theta has to remain constant. So accordingly, we can see that with increased field current, EA is increasing, and this will keep on increasing. While as what is the case with IA is that IA will shift from lagging power factor to leading power factor, and that will actually make uh, the armature current to rise with the field current. So initially we had a lagging power factor, and then we have a leading power factor. So this is actually known as the V curve of synchronous motors. We are getting a V-shaped curve where we are seeing that IA decreases with respect to field current in the lagging power factor region. It is minimum value at power factor equal to 1, and then it starts increasing. Now if we change the power, if for different values of power, depending upon if P is this is corresponding to uh, lesser amount of power, this is corresponding to a greater real power. So the curve will shift upwards. We can have these different curves, and there will also be a slight change in the power factor, unity power factor region. Initially, unity power factor was at this field current. Now the unity power factor will be at this field current, and the unity power factor will be at this uh, current. Here actually now what we are doing is we are increasing IA cos theta, and accordingly at a different IA cos theta we will be getting a different curves. So with different values of real powers we can the curves will vary like this, but at a constant power factor the curve will vary like this. IA varies with respect to IF in a V-shaped manner. So this is mm, referred to as a synchronous motor V curve, and it uh, It helps us understand how IA changes with respect to IF, the armature current, how armature current changes with respect to field current in a synchronous motor. We are not talking about a synchronous generator. We have already seen IA versus IF is a linear curve in a synchronous generator. Uh, you may also note this that at points where EA is less than V5, the motor is said to be under excited. At points where EA becomes greater than V5, the motor is said to be overexcited. So these may be noted about the synchronous machine or about any machine. You have a larger amount of field current, the motor is said to be overexcited, and a smaller amount of field current means smaller amount of EA will mean the motor is underexcited. So, what other information can we say can we get from this V curve is that about the reactive power of the system. Uh, for field currents greater than the value, we have seen the armature current will be leading at sometimes, and for field currents less than the less than some particular value, the armature current will be lagging. So at lagging power factor, we know that the synchronous motor will consume, or we understand that anything consumes reactive power. So for the lesser the amount of field current, the lagging nature of current means more amount. Lesser the nature of field current means here that the armature current is much larger, but it is in a very it's in a lagging power factor region where it will start consuming reactive power. As the field current is increased, the armature current is decreases, but the power factor becomes unity. Uh, and if we further increase the field current, armature current again starts increasing. But in the leading power factor region, that means now the synchronous motor will start this supplying reactive power instead of being a consumer of reactive power. So synchronous machines, uh, synchronous motors rather, they are used for reactive power compensation because of this very nature that they can supply the reactive power as well as they can consume the reactive power depending upon the mm, depending just by varying the amount of field current supplied to the synchronous motor. So this finishes our session. We'll look into some miscellaneous topics about synchronous machines in the next session.